substitution. It is a fundamental organic reaction where one atom or group, the nucleophile, will replace the another atom or group, the leaving group, on an electrophilic carbon atom, which is a substrate. This is the key for forming new carbon heteroatom bonds like C double bond O, C double bond N, C double bond S, and so on. Okay, there are two main types of it, which is SN1 and SN2. SN1 is a stepwise mechanism and SN2 is a concerted mechanism. SN2 reaction condition and characteristic. First of all, for the starting material, the substrate preference is metal halide, primary halide, secondary halide, and tertiary halide. But the tertiary one rarely react due to the stereoanhydrous. Okay, for the nucleophile, the more favored to use is a strong nucleophile, which is OH minus, CN minus, CH3O minus, and RSH, and so on. Okay, for the solvent, polar apatite solvent are more preferred, like DMSO, acetone, DMF, acetone natural, and many more. For this stereochemistry, if the starting material to be used is a chiral center mesh, the inversion of configuration will happen, which is a Walden inversion. So, first is reaction. The backside attack are crucial, which is one mechanism for SN2 reaction. We can see that the starting material is a metal halide, and we can see that Br is our leaving group, and OH is a strong nucleophile, and it's favor SN2 reaction. So, it will attack the starting material from the backside, and they will undergo in the transition state, and because of that, the bond between carbon and bromine will be break. So Br minus will leave the group, and the final product we can see that it is opposite from the beginning because it undergoes inversion of configuration because of OH is a bulky group, so it will push the other one to the
SN1 reactions happens in two steps. Step 1 is the slow rate determining steps. Here, the leaving group, in this case Br minus, leaves and form a carbocation intermediate. Step 2, which is K2, is much faster. The nucleophile, like H2O, attack the carbocation. In step 3, we get the final product after the proton transfer, which is the hydronium ion. Notice that K1 is much slower compared to K2 and K3, which is why step 1 controls the reaction rate. SN1 reaction works best with the substrate that can form stable carbocation, which is tertiary carbocation. Primary carbocations are too unstable, so SN1 rarely happens with primary carbocation. For solvent, polar protic solvents are preferred because this can stabilize both the carbocations and the leaving group. For example, water, ethanol, methanol, and acetic acid. Since the carbocation is already very reactive, SN1 can use weak nucleophile like H2O, CH3OH, CH3CH2OH, or fluorine. If the reaction happens at chiral center, you will get a mix of both enantiomer, meaning the product is a racemic mixture. Let's start with SN2, Benadryl. Benadryl is a common antihistamine used for allergy relief. During its synthesis, an important step involves an SN2 reaction. This helps form a crucial tertiary amine linkage in the molecule. SN2 reactions are perfect for this because they are clean, straightforward, and don't involve messy rearrangements, which is great for synthesizing drugs with precise structures. What about SN1? SN1 reactions are used less often in pharmaceutical synthesis, mainly because they involve carbocation intermediates, which carry a range and lead to unwanted side products. But in specific cases where the carbocation is stable, SN1 reactions can be useful. For examples, in the synthesis of certain local anesthetics or tertiary alcohol-based APIs. Let's take a look at how SN1 and SN2 reactions are actually used in real-world industrial chemistry. First, SN2 in ether synthesis. We use the Williamson ether synthesis, which is an SN2 reaction, to make unsymmetrical ethers, like diethyl ethers. Diethyl ether is an important solvent in both laboratories and industry because it is highly volatile and can dissolve many organic substances. In fact, the global market for diethyl ether was about $1.5 billion in 2022, proving just how useful this SN2-based reaction is. Next, SN2 in nitrile synthesis. Another SN2 application is the synthesis of nitrile. Here, a halide is substituted with a cyanide ion to produce a CN group. For example, bromoethane can be converted into acetonitrile. Acetonitrile is a super important polar appropriate solvent, and it's also a precursor for making polymers and used in HPLC analysis. Its global market is around $600 million in 2023.
And relevance of this topic we can see from the formation of carbon heteroatom bonds. It is a fundamental for creating diverse organic molecules that replace living groups with alcohol, ether, amine, cycles, and so on. Okay, for the biological relevance, this concept of nucleophilic attack or living group departure in enzyme catalyzed reaction. For example, like methylation reaction, acylation reaction. Okay, for the building block for complex molecule, we can see that it's a crucial step in multi-step synthesis of pharmaceutical, agrochemical, and natural product. And like we know, around 25% of all commercial organic reaction they involve this nucleophilic substitution. For the environmental context, there we need to be understanding fate and persistence of pollutant like hydrolysis of organoid.